and then we'll give it a few minutes to let everybody in. So welcome everyone. Let's see. Okay. Yeah, it'll probably go off when we get started, but that's okay.
Okay. And I have an hour, right, Sarah? Okay.
Yep. Okay, well, we'll get started, and I'm sure there'll be a few others joining in. So hello, welcome to today's digital lunch and learn called Mars 2020 Mission Update. And if I got that wrong, let me know. So with further ado, please welcome alumni Tom Durkin, Geology 86, to talk about the Mars 2020 update. And then just so everyone knows, my name is Sarah Bonai. I'm the interim alumni director here at CARA. And just some housekeeping things before we get started. This event will be recorded and uploaded to our YouTube channel afterwards, so it might take a couple days. And then we always like to know who's here. So in the chat function, just make sure you switch it to all attendees and panelists and just say hi, your class and major, just so we know. And then without further ado, please welcome Tom Durkin.
Well, thank you, Sarah. I appreciate it, and I'm glad to be here. And I won't monitor the chat. I don't think I'll be able to, but like if you see questions that come through the chat that maybe you can even turn them on so I can hear them, later, that's fine. But you can let me know if they're okay. Great, thank you.
Yep, Q&A and chat. So please, if you have questions or anything, just drop them in the Q&A and chat, and we'll watch for them.
Great. I'll just go ahead and share my slides here, and let's see. Can you see them now? I'll assume you can.
Yes, I can.
Okay, very good. All right, so we're gonna take a little trip to Mars today and give you an update of the Mars Perseverance rover mission. So thank everybody who came. I thank you and welcome. Just a little bit about myself, I guess. I've been working here at the School of Mines now for about 22 years. I graduated, as Sarah said, with my master's in geology in 1986 and worked for about 12 years in Pierre for the DENR, which is now the DANR, for the state mining program. And then in 1999, I came back here to work for the NASA Space Grant Program at the School of Mines and been here ever since. So part of our job, it's mostly higher education, working with the students who want to work for NASA or aerospace and do internships at NASA and things like that when they're students. We have a big fellowship program. We do have an outreach to K through 12 and the general public. So this is a talk actually that I just gave a few days ago at the Badlands Astronomy Festival over this past weekend. So I'll just kind of repeat that talk for you folks. So on February 18th, we had the Mars Perseverance rover, one of quite a few rovers in line that have gone to Mars, successfully land. And this is an artist's drawing of the descent stage, literally just a few tens of feet above the surface of Mars as the rover is being let down on a cable that drops about 20 feet from the bottom of the descent stage and then touches down on the surface. And this is the moment of touchdown, another artist's view. At that point, the cable gets cut, the descent stage flies away to a safe crash point so that, of course, it doesn't come straight down and land on the rover. And then this is just another drawing of the rover after it released the little mini helicopter that it was carrying with it on the underbelly of the rover. And we'll talk a little bit about that helicopter in a minute. Its name is Ingenuity. Okay, so this is the very first image taken from one of the cameras on board the rover, literally seconds after the rover landed. And then, of course, it was sent back to Earth. There was about an 11-minute transmission time at the speed of light to get back to Earth. But this is actually the first image that the rover took just a few seconds after it landed, showing that it landed on its feet and is right side up. And of course, NASA mission control, at least the mission control for these rover missions out in Pasadena, California, erupted with a big celebration. You can imagine the tense feelings everyone was going through during what they call the 7 minutes of terror, which is the 7 minutes that the lander is descending through the very thin Martian atmosphere, having to slow down from about 12,000 miles an hour to near zero for a successful touchdown. And everything had to happen autonomously for that to work right. So as soon as they're actually looking at that picture that I just showed you at the moment of this celebration. So here we see the launch of Perseverance, which was just about a year ago, actually, July 30th of 2020, being launched from Cape Canaveral Air Force Station, which basically is Kennedy Space Center down in Florida. The rover is on the top of that Atlas V rocket and launched at 7:50 in the morning. It took about 7.5 months to reach Mars. The Perseverance rover is the most sophisticated rover NASA's ever sent to Mars, and its name embodies NASA's passion and our nation's capability to take on and overcome challenges. Perseverance. It will collect carefully selected rock and sediment samples for a potential future return mission to Earth. And we'll talk about that in a minute. But its main science task is to search for signs of ancient microbial life that may have existed on the surface of Mars at one time when it was much wetter and much warmer than it is right now. And then the rover also has a lot of geological sensing equipment on it to tell us more about the planet's geology and climate. And of course, it paves the way for eventual human exploration to another planet, which we've never done. That'll be something. And we've been to the moon, but we've never set foot on another planet. And it looks like Mars will be that planet when we do that. So if we could size up Mars and Earth and put them right next to each other, this basically is what they'd look like. The diameter of Mars is just about half of Earth's. It's about 4,200 miles, whereas Earth's diameter is about 8,000 miles. So being smaller, it's obviously less massive, only about 1/10 of the Earth's mass. When that equates to gravitational attraction, Mars has only 38% of Earth's gravity. So you lose weight really fast when you go to Mars. It is very cold on Mars. The average temperature is minus 64 degrees below zero. That's average, planet-wise and throughout the year. That's about as cold as it can possibly get in Fairbanks, Alaska. But it can get much colder on the poles, the Martian poles, in the wintertime, where it gets down to almost 200 degrees Fahrenheit below zero. And it can get warm, about as warm as today in the middle of the daytime on the equator in the summer, about 80 degrees Fahrenheit. So you can see there's a much larger temperature swing on Mars than there is on Earth. A Martian day is the most similar to our own Earth day of any of the planets in our solar system, about 24.6 Earth hours for Mars to rotate once around its axis for one Martian day. And a Martian day is called a SOL, S-O-L. It takes almost twice as long to orbit the sun, about 1.9 Earth years for one Martian year. It can be windy and it can be perfectly calm. The winds can get up to about 80 miles an hour. And it's interesting to think about what that might feel like, because Mars has an extremely thin atmosphere. Only about, it's actually a little less than 1% of Earth's atmosphere. And the little bit that's there is almost entirely carbon dioxide, about 95% CO2. So when you think about a windy day when the wind gets up to 80 miles an hour, it wouldn't feel like 80 miles an hour on Earth. You'd barely be able to stand up to an 80-mile-an-hour wind on Earth, because that's hurricane force. And so with only 1% of the air molecules pushing against you on Mars, it would feel quite a bit different, and I don't think it'd be any problem to stand up to that wind. Mars has 2 moons, and then 2 prominent geologic features I'll mention is there's the largest volcano in the solar system on Mars. It's called Olympus Mons. It's now an inactive volcano, but it's about 16 miles high, which makes it about 3 times as high as Mount Everest. It's very wide, extremely wide, and if we were to plop it down on Earth, it would just about fill up the entire state of Arizona. And then there's a huge valley on Mars. You can see it actually here, if you can see my cursor in this image of Mars here. And a close-up is this. It's called the Martian Valley or Valles Marineris. On average, it's about 4 times as deep as the Grand Canyon, about 4 miles deep. So a much deeper and longer canyon on Mars. Now, we mentioned the atmosphere. These are 2 actual images. The one on the left is obviously Earth's atmosphere, looking down at the atmosphere, down into the clouds, taken by one of our astronauts out the window of the International Space Station. And on the right, we see the Martian atmosphere, taken by a robotic spacecraft that is orbiting Mars right now without people. And it's taken during a windy time, during a dust storm. So that orange-colored, rusty-colored soil, dust, gets blown up into the atmosphere and actually makes it visible. If it wasn't for the dust storm, we wouldn't even really see the Martian atmosphere in this image. I'll mention 3 of NASA's orbiters that are going around Mars right now. The first is the Odyssey, which got into orbit around Mars in 2001, and it basically maps the elemental composition of the surface. It can provide information on structure of the surface and the geological processes that formed those structures, those topographical structures. It also measures radiation to evaluate risks to people when we send that first human mission to Mars. Then we have what I like to call the workhorse, which is the MRO, or Mars Reconnaissance Orbiter, which has been doing very well ever since 2006. It has a very powerful telescopic camera on it, and NASA uses it basically to find good landing sites. That's one of the things it uses it for. It can resolve features on the surface down to about the size of a kitchen table. All of these orbiters are about 200 miles up above the Martian surface. The MRO characterizes the climate, seasonal changes in atmosphere, and it also looks at geologic features. It can look for water ice on the surface and the subsurface, and it has a very fast data relay capability to send those images and that scientific data back to Earth. And then lastly, there's MAVEN. It's kind of a mouthful, but it's the Mars Atmosphere and Volatile Evolution Mission, which basically gives us more information on the Martian atmosphere and the types of elements that are in the atmosphere. As I mentioned, CO2 makes up the majority, about 95%. So obviously, the science team at NASA has a variety of tools at its disposal, starting with these 3 Martian orbiters, which have all been collecting images and data of this particular landing site of Perseverance from about 200 miles up. But to search for signs of ancient life on the surface, that requires a much closer inspection, and is why we have to send the rovers to the surface. So this is just a schematic. It's a flattened out map, basically, of Mars surface, and it shows all of the NASA landers and rovers that have been sent to the surface. The 5 that are circled are the rovers. They have wheels, they can drive around on their own. The ones without the circles are the landers, which just have legs, and they have to carry out their science missions from one spot. Perseverance landed in a large circular crater about 28 miles in diameter called Jezero Crater. We'll see some pictures of it in just a minute. and it landed about 2,300 miles away from the Curiosity rover, which is very similar in looks to Perseverance. Both are, if you will, nuclear battery powered, not solar powered, so they can generate electricity anytime throughout the day or night. I'll show you some pictures from Curiosity also, because it is still operating. It landed in 2012. So it's very hard to get to Mars. And if we want to think of it as like a game, here we see a halftime score between the two competitors, Earth on the left and Mars on the right. And Mars is winning this game. There have been a total of 48 worldwide missions to reach Mars. That can either be through landers, rovers, or orbiters that don't land but need to successfully get in orbit around Mars. Out of those 48 times, 26 of them have been failures, okay? And the countries that have sent or attempted to send landers or orbiters to Mars are 7 of them. It's the US, the USSR, Japan, the European Space Agency, China, India, and then just this past February, the United Arab Emirates. 22 of those have been successful. So if you like baseball and you like to think about success in terms of a batting average, that's a batting average of 458, which is amazingly good when you think of how hard it is to get a spacecraft all the way to Mars. The analogy that I heard for Curiosity was that if you looked at the targeted landing zone that Curiosity had, which was, if I remember right, something on the order of, I can't remember, but it was an oval with a long axis somewhere on the order of about 20 some miles. If you thought of that oval as the eye of the needle, and you were trying to thread that needle from Earth, it would be equivalent to having the needle in Sturgis, and you're trying to thread it from the campus here at the School of Mines. So that's the pinpoint accuracy in just a simple analogy like that to show how difficult it is to do it. So 458 is very good. Now, if you just look at the United States batting average at attempts to get to Mars, we're much better. We're batting 739. So we have been successful 17 out of 23 times, which is astounding, really. So I mentioned the main mission is to search for signs of ancient life. That's Perseverance's main mission. Previous missions have shown us pretty much beyond a doubt that Mars once hosted running water, liquid water, before becoming what it is today, and that is a frozen desert. So earlier in its history, Mars had much warmer environments at the surface that could have possibly supported microbial life. So Perseverance is taking this next step, seeking as its primary goal to answer one of those key questions of astrobiology. Are there signs or biosignatures of past microbial life on Mars? And to answer that question, NASA put in a new suite of high-tech, cutting-edge instruments to tackle that question from several vantage points. What I'm going to do now is I'm going to try to share a little video that, let's see if this will work for me. It's less than a minute long, and let's see here. Where is it? Show all windows. Here we go. I'll try sharing this one. This shows the descent stage and everything that had to happen in exactly the right sequence during the 7 minutes of terror once the spacecraft reached the top of the atmosphere and had 7 minutes to slow down enough for a safe landing. So I'll just go ahead and play this Okay, actually, I played the video that I was going to play later, but I'll just go ahead and let it finish. And I'm just kind of playing these out of order, but I'll explain that in a minute. I'll just go ahead and finish this video.
Is there sound with the video, Tom?
Oh,
Tom, this is Dane from the ITS department. If you click on just the new share option there, it opens that window. And then in the bottom left, there's two check boxes. One of them that includes sound with your video, and then another that optimizes for video play. Do you see those?
let's see. I'm looking at the bottom right. I don't see anything on the bottom left.
Do you have the window open that has, your screen share options and all the different applications? Is that what you're looking at?
Let me do that. Okay, it does now. Yeah.
Yep. So if you activate those two check boxes, it should share the audio with the audience.
Okay, so do I need to stop the share to do that?
You can just do, if you have those check boxes active and then you hit share again, it should just activate that stuff for you.
Okay, let's see. You know what? It's going to take me a while to figure that out. Sorry about that.
No worries.
I had these embedded in my slides, so they played automatically. And for some reason, it worked at the Badlands, but it's not working here. So let me just go back to the slides, I guess, and we'll just forget about the video. Let's see. Okay, because that video really was just a summary of some of the things that I had planned on, mentioning in the slides. So let's see here. Back to slideshow mode. Okay, so we'll touch on all of those things. But this is a schematic of the video that I wanted to actually first wanted to play, the one that was less than a minute, and it just compresses those 7 minutes of descent into less than 1 minute. But you can see that schematically here. So at the upper left, when the rover touches the top of that thin Martian atmosphere, it's traveling about 12,000 miles an hour. So it's still hitting that thin atmosphere and building up friction. So the temperature gets up to about 2,500 degrees C, and the atmosphere will slow it down significantly as it passes through more and more atmosphere as it's descending. Once it gets to about around 1,000 miles an hour, which is still about 8 or so miles above the surface, supersonic parachute deploys, slowing it down more. At that point, the heat dissipates and the heat shield can jettison from the spacecraft. At that point, the spacecraft now has eyes, and it can sense the surface with cameras and radar to determine how far it is from the surface, and it can also move itself depending on obstacles that it sees below. This is the first time a NASA descent stage had this capability. It's called terrain relative navigation. And the reason that NASA built it into this particular mission is because the landing target zone is a very unfriendly landing area. As you saw in part of that video that I'll show in a picture in a minute to explain more about it, but we wanted to land this rover in an area of an ancient delta, river delta, where we think conditions could have been very good to support microbial life when there was water flowing into this 28-mile wide crater through a river system. And at that point, it was a lake. It was a crater lake. And so there are cliffs at the side of the delta. There are large rocks and boulders. There are obviously holes from subsequent meteor impacts and all sorts of hazards. So this terrain relative navigation allowed the onboard cameras now to be able to take very high resolution images of the surface that we wouldn't be able to see from the orbiting orbiters 200 miles up. And they then can move the rocket or the descent stage up to 2,000 feet in any direction from the point at which it would have landed if it just came down along the trajectory that it was taking. So it's a very useful technology, and basically the descent spacecraft can think for itself now, and it's looking for the absolute flattest, clearest possible landing zone within this relatively circular, somewhat oval target zone of about 4.8 miles, okay, almost 5 miles. That's anywhere in that zone they wanted to land in the flattest spot that they could find. And that's what you're seeing here is going on at this point. Then at just about 200 miles an hour, the parachute has slowed the descent stage down to that point. The parachute breaks away and the descent stage separates from the back shell. The retro rockets kick on, and it's now a powered descent to the surface. 60 feet above the surface, they deploy what they call the sky crane maneuver, which drops the rover on a 20-foot cable, series of cables, below the descent stage. And then it just slowly goes down to the surface. And as soon as it senses that the rover has touched its wheels on the surface, that those cables cut and the descent stage flies away off to the side here, and the rover is on the ground. So again, they call that the 7 minutes of terror. Everything had to be pre-programmed to happen at exactly the right sequence, because at the point that it touched the atmosphere, it takes the speed of light 11 minutes to send a signal back and forth to the spacecraft. So it had to land completely autonomously, and it did so very successfully on February 18th. And this just is an actual picture taken by one of the European Space Agency's orbiting spacecraft called the Express Orbiter. And you can see the outline of Jezero Crater here. And this is the targeted landing zone, that 5 mile an hour or 5 mile diameter oval. And this is the delta right here. So again, we think that perhaps fossil evidence of ancient microbial life might have been preserved in this delta. You can see where the river channel came in, broke through the wall of the crater, deposited its sediment. This is now filled with a lake. And as you saw a little bit on the video, there's an exit point on the other side of the crater. This is the way, this is what happened about 3.5 billion years ago when Mars had a much thicker atmosphere and warmer climate. So that's an actual image. This is the picture you saw in the video where the river's coming in, depositing the sediments that had eroded from the surrounding landscape here in kind of a bird foot delta, just very similar like the Mississippi River Delta. And then over here, the water is exiting. And this is an image taken from our own Mars Reconnaissance Orbiter, showing a coloration difference to show different aspects of the elemental makeup of the sediments here, but you can see here's the bird foot delta sort of looking. And again, you can see, in here, you wouldn't want to land right where my cursor is, because if you did, the rover would fall down a cliff. So again, it was a very, it worked flawlessly, and they found a nice, flat, safe area to land. And this is just kind of a 3D image just showing a potential path that the rover could take as it's investigating these ancient river delta sediments as it comes on up actually to the lakeshore of the rim of Jezero Crater. Perseverance is designed to drive on average about 650 feet per day. To put that in perspective, the longest drive in a single day by any rover previously was 702 feet, a record set by the Opportunity rover. So Perseverance is designed to drive that amount almost every day, just a little short of that. And of course, there'll be days where it goes much farther. It has its own self-driving capability, kind of like a smart car. And rather than us having to send signals up every time we wanted to turn right or turn left to move around an obstacle that its cameras have told us are in front of it, the rover can make those decisions for itself. Now, what could some of those ancient microbial life forms look like? Well, on the left here, we see rocks along the shoreline of Lake Salda in Turkey. And these rocks here in the image are actually formed by microbes that trapped minerals and sediments in the water, sort of like stromatolites. Stromatolites are, for the most part, at least the kind that existed in the fossil record, are no longer present on Earth, but yet we see their fossil remains. This is a fossil stromatolite collected at the Pilbara Craton in Western Australia. So the rover will look for features like this as it is exploring the surface of Mars. And if they find something like that, it would be relatively hard to attribute it to anything other than ancient microbial life. But those are the kinds of things that NASA will be looking at very carefully. And of course, also sampling with the rover for potential return missions to Earth in the future. And so, what do the rovers look like? Well, here's kind of an evolution of the rovers through time. These are exact duplicates of the rovers that went to Mars, but they're outside in what they call the Mars Yard of NASA's Jet Propulsion Laboratory in Pasadena, California. And this is Curiosity, the one that looks very similar to Perseverance. It's just under a ton in weight, with quite a few scientific instruments on board. This is one of two identical solar-powered rovers about the size of a golf cart. One was called Spirit and the other was called Opportunity, and they both landed on Mars in 2004. And then here in 97, the Mars Pathfinder mission brought with it a little robot that I could pick up and hold in my hands called Sojourner. And it also, you can see the solar panel, its solar panel. This is Perseverance. And you say, boy, it's almost an exact duplicate of Curiosity. Well, it's a little bigger, it's a little over a ton, and it has more sophisticated scientific instruments on board of it. Both of these rovers are powered by RTGs, which are radioisotope thermoelectric generators, which basically can be thought of as a nuclear battery. They each contain about 10.5 pounds of plutonium, which upon decay gives off heat. So just like the name states, the radioisotope is the radioactive material, the plutonium. Thermoelectric, well, what it does is it takes that heat and converts it into electricity that then generates and recharges two roughly 30-pound lithium-ion rechargeable batteries. They supply the power to the rover. And basically, we think that at the rate at which the plutonium decays, if nothing else happens to Perseverance, that battery will be able to provide enough power for this rover to do what we want it to do for the next 14 years. And this is just a schematic showing that the 7 scientific instruments. I won't spend a lot of time on this, but we'll start up at the top. The Mastcam Z is a very advanced camera system, a very high resolution. I think it's a 20 megapixel camera that can take extremely high resolution images of samples and rocks and sediments that the rover is sampling. And then the SuperCam up here basically is it can provide analysis of chemical and mineralogical compositions of the rock samples. It can also look for the presence of organic compounds. And then there's Pixel over here, which is on the end of the robotic arm of the rover, and it stands for Planetary Instrument for X-ray Lithochemistry. Basically, it's an X-ray fluorescence spectrometer with an imager. And it also looks at elemental compositions of Martian samples. Then there's Sherlock, which I kind of like to think sometimes they come up with these acronyms and then develop the words to describe what they are, but it's a real mouthful. It's the Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. So it too is a spectrometer, and it can use an ultraviolet laser to zap the samples and determine fine scale mineralogy and whether or not there are organic compounds. And then there's just a couple of proof of concept experiments. MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. Basically, we just want to see if we can manufacture oxygen from the thin Martian atmosphere and the little bit of CO2 that's there. Obviously, we would need that when we do human exploration on Mars, and we'd also need it possibly to produce liquid oxygen for rocket fuel. So that little experiment is just to see how effective we can manufacture oxygen from the Martian atmosphere. And then I think I'll just I'll skip the META, and then the RIMFAX is like a ground penetrating radar to look at geological structures under the surface. And then we talked about the helicopter, the little Ingenuity helicopter. It was the second proof of concept experiment. It's basically a ride along. It had no other purpose other than to see if we could demonstrate controlled, powered rotorcraft flight on another planet, which had never been done in the past. So again, the atmosphere is extremely thin, so it'd be very hard to fly something in that atmosphere. So NASA just wanted to see if we could do it. So it built this very lightweight helicopter, Ingenuity, about 4 pounds. It brought it along, attached to the rover. Shortly after landing, it dropped the, it deployed the helicopter legs. It dropped it from the bottom of the rover. It drove over the top of it, careful not to crush it, and then drove away to a safe distance, turned around, and started taking pictures and videos of it. I believe it was in April when they had the first of a planned sequence of 5 test flights. We have now flown Ingenuity 9 times, so it has far exceeded its original plan and its original goal. There's two sets of counter-rotating blades, each spinning at about 2,400 RPM, and it worked. It flew in that thin Martian atmosphere. So that was really a historical moment, kind of reminding us of what we did back in 1903 when Orville and Wilbur Wright first got off the ground in their airplane at Kitty Hawk, North Carolina. So it's 117 years later, and we did that not with a person on board, but with a robot on another planet. So you can see here in the picture on the right, I believe that's Orville flying, laying on top of the plane here with Wilbur looking on. And they're just a few feet above the surface. Over here to the left is the picture that Perseverance took of Ingenuity before its first test flight. And if you look closely at this, this is actually a little video that's playing. And you can see that this is the first test flight in April of 19th. And it's actually hovering about 10 feet above the surface of Mars. So that first flight was just an ascent to 10 feet, to hover for a short time and come straight back down. And it worked. This is a picture of the second flight. It's actually above the surface. You can see the counter-rotating blades a little better in that picture. This is a picture of the third flight. You can see it up in the air a little higher than 10 feet. It's over a rougher area now too. So they started flying it horizontally also. This is a picture after it landed after its 8th flight just last month. And then this was one I downloaded just before last weekend for the Astronomy Festival. I didn't actually get a picture of it after the 9th flight, but on July 5th, it flew actually a much longer distance than it did on any of its previous 8 flights, which are shown by the green lines here. And it went actually a little over 2,000 feet on that 9th flight over a much rougher area, taking pictures of areas where NASA may want to send the rover. So what do the rovers look like in reality on the surface? This here is a selfie that Perseverance took of itself. You can see Ingenuity just a few feet away. This was taken on the 46th Martian day after landing. You can see where it had driven. The camera on the robotic arm actually took a series of about 62 separate images of the rover from different vantage points, moving that robotic arm around. And then in each of those images, NASA removed the robotic arm from the image so that the composite shows the entire rover. So it's a selfie. And then this is a selfie that Curiosity took of itself in 2016. You can actually see where it did a little bit of drilling with the onboard drill to analyze the samples that came out of that drilling. And this just shows some of the layer cake geology. This is a picture that Curiosity took. It also landed in a large crater called, let's see, the crater name escapes me right now. Let's see, Gale Crater. And in the middle of Gale Crater is a mountain that's called Mount Sharp. And it also was filled with water at one time. So these sediments were laid down sequentially, kind of like layer cake geology. And it just is interesting. It looks a lot like the Grand Canyon to me, when you look at the stratified layers that have since been eroded and forming these landforms. And then I also have a couple slides in here that I threw in for the Badlands Astronomy Festival, just showing a picture that I took not long ago of Sheep Mountain Table down in the Badlands, which also reminds me a lot of the layer cake geology here on Mars. And of course, I had to throw in a picture of my own rover that I used to get there. And then a picture from the top of Sheep Mountain looking down. Again, a lot of similarities to the geological features between the Badlands and the Grand Canyon and Mars. As just an outcrop, I won't spend time on this one, but just shows you how the scientific instruments here can analyze the rock outcrops. This one also was taken by Curiosity. Here we're looking at some fracture fill, where in this case, the sedimentary rock, it was laid down in a water environment. The water then left, the rocks hardened and lithified and then cracked. And then a subsequent wet period came through where there was groundwater that were rich in minerals, dissolved minerals, that seeped into those cracks and precipitated out the minerals to fill the cracks. In this case, we're looking at calcium sulfate, basically, which is gypsum. And this is a sample on Mars. And then we can compare, here's a sample on Mars. We see the fracture fills with hydrated calcium sulfate, which is gypsum, and an Earth equivalent sample over here. Here's some cross bedding taken by Curiosity, evidence of stream flow, geologic cross-section, just like you would see if you went drove up the road to Dinosaur Hill and see the Dakota sandstone formation where we can see this cross bedding. And this is almost my last slide. This is just an artistic slide that I just thought was really pretty. This one also was taken by the Curiosity rover. It's actually crossing an extremely large dune that takes up this entire image. And then on the surface of that large dune, there are secondary and tertiary ripple marks. And it's interesting because the larger ripples, in other words, the secondary ones, the ones that look like waves, have distinctive sinuous crest lines and are a type of ripple never seen on Earth nor previously recognized on Mars. So to see this level of detail, we can't resolve this from the orbiters. You have to have a rover on the ground. And I have no idea if the reason these ripples are different on Mars compared to Earth. I'm not sure if this is the reason, but I'm just guessing it may have something to do with the very thin atmosphere. And so when the wind blows in a very thin atmosphere, it may form those ripples differently than our wind does here on Earth. But I just think it's kind of a pretty picture. It reminds me of like sitting on a rowboat out in a big lake or the ocean, and it just looks like waves in the background. So here is where I was going to play that video that didn't work as an ending, but I'll just go ahead and end now and ask for any questions or comments. Thank you.
Thank you, Tom. Yes, if you have any questions or comments, please put them in the chat section, and we'll watch for them. Chat section or the Q&A section, sorry.
Do you have the capability of turning on people's speakers, or do they have to send them in on chat?
We can turn their speakers on. We can pull them in if we need to.
Okay.
Oh, what is the future for this mission? What's next?
What's next? Okay, what the future for this mission is to continue doing the things that I mentioned are in the science goal. So now that we actually had more success with the Ingenuity helicopter, so Perseverance hasn't been doing quite as much of the science end of things and analyzing the rocks and soils as was originally planned, because the helicopter worked so well. They wanted to continue testing it in different environments for longer flights, making different maneuvers in the air and that type of thing. So it actually just kind of put a little bit of hold on the traveling of Perseverance. But now I believe they're really focused on more of the geological and potentially paleontological investigations from now going forward. So we'll hear more along those lines. But for what's next then, what the video would have said had the sound been on, you would have heard them talking about two actually additional missions in the future that are right now only in the development stage, but it's to potentially return some of these samples. So some of these samples that are taken by the rover are being encased in cases that will preserve the samples, and they're being left on the surface in these cases. They're being cached, okay, and left on the surface. The idea is that a future mission would launch to Mars robotically, land. It would have on board a capability of, when I look at the item and I see a picture of it, it looks kind of like a mortar launcher. But there would be first a rover that would go out and collect the cache of samples, bring it back to the launch vehicle, which is a tube about this long. The samples would be placed into them, and they'd be launched almost like a mortar up into the atmosphere, and they would then dock with an orbiting spacecraft that would bring those samples back to Earth by, right now, they're thinking 2031. So That's only in the planning stage now. But the point is they're analyzing and getting all the information that they can on those Martian samples, just like Curiosity has been doing ever since 2012, and sending that information and those images and pictures back to us so that we can get that level of detail. But even if we found something that looked like fossil stromatolites, you'd want to analyze them in an Earth-based laboratory. So it's much better to have those samples physically in your presence. So that's the idea of the next stage for this particular Mars 2020 mission, to bring those samples back maybe by Mars 2030, actually 2031.
What is the expected lifetime of this rover?
So the lifetime is if nothing mechanically goes wrong with it, and they're very well built, Curiosity still operating like the day that it landed, mechanically, if nothing goes wrong, it'll depend on the RTG, the nuclear battery. And at the rate at which, as I say, the plutonium decays, the plutonium-238, it should be able to provide a maximum of 900 watts of electrical power, which is what's needed during maximum scientific instrument data collection for 14 years. But oftentimes, these rovers exceed expectations and last a lot longer. So, but anything could happen. You know, anything could happen. There could just be a breakdown of something mechanical, like sort of what's going on with the Hubble Space Telescope right now that they're trying to figure out. It could be a breakdown in computer. It could be a broken wire. Who knows? You know, there are G-forces still that are exerted on the spacecraft, but fortunately, it looks like nothing was damaged upon travel and landing. So hopefully, the electronics will continue to work. But anything can happen. You know, anything could happen. It could get hit by a meteor. But anyway, if nothing mechanical breaks down, we're hoping for at least 14 years.
Robert, how we can for sure, Tom can share the video. We'll get the PowerPoint and the videos to you so you can show it.
Oh, great.
That's what he's wondering. And then, yeah, both videos. And then the other question he has is, have they found a way for man to survive the radiation for a trip to Mars?
Okay. So the first question is, yes, I'll send the two. I actually have the two video files, so I'll send them to you and Dane. And then when you upload the slide, maybe you could just also they're big files, but you maybe could upload them and people could just click on it and play it themselves. And then the second question was on radiation. Yes, actually, one of the biggest, longest term experiments that we continue to do on the International Space Station is looking at how we can protect our astronauts from long-term radiation exposure. And that's the reason, really, that 6 months is the maximum for any astronaut that is conducting a mission on the station. We did have an experiment where one astronaut went up for a year, but that kind of took special permission to look at the effects of radiation and other things associated with microgravity on his body. But so the answer is yes. We're continuing to develop ways of keeping astronauts safe. There is a place in the space station where astronauts can go for cover, if you will, during a coronal mass ejection, where electrified gas is shot out from the sun. If it happens to shoot it out toward Earth, and of course would impact the International Space Station, which is above the atmosphere and not, doesn't have the protection that we do on the surface just from our atmosphere and magnetic field from radiation. They can crawl into this area and let that coronal mass ejection pass on by as the solar wind basically blows it by the. In other words, it travels at about the speed of the solar wind, and it's a burst. So you would want to take cover while that radiation wave passes through. So those are kinds of things we could do. We could look at having those types of safe houses, if you will, on board a spacecraft that's in the middle of a 7.5 month or 8 month journey to Mars. And then also what we did not do in the Apollo mission, and that's why I tend to be on the school of thought where we need to go back to the moon and set up a lunar base before we go to Mars, because if we don't just do a flyby of Mars, an orbital mission, and then swing back to Earth, kind of like Apollo 8 did before we landed on the moon with Apollo 11, swung around the moon and came back, it may not even be logistical to do that, because you have to kind of wait for Earth and Mars to realign themselves, for the shortest potential trip to and from each planet. And so the shortest period right now is about 7.5 months. And that window for launch only opens up once every 2 years, because Mars's orbit is about 2 years around the sun. So for all practical purposes, those astronauts will probably have to stay on the surface for quite some time, not just a few days like they did with Apollo. And you will need protection from radiation when you are in a Martian base. So those are all things that NASA is working very hard at trying to answering those questions of how can we keep the astronauts safe from radiation. It's really one of the biggest risks with long-term space flight. So that was a good question. Long answer, but good question.
So we had another question. From Richard Miller, if Mars' atmosphere is 95% CO2, why isn't the surface temperature warmer? And he says, I understand it's further from the sun, but Earth's atmosphere is only 0.04% and is being blamed for extreme heating.
That is so interesting, because I had that same thought, and I have asked different people. I'm not an expert in this area, but I wondered the same thing. I mean, it's less than 1% atmosphere, but the CO2 is 95%. And here on Earth, it's something like 0.03%. Even though we have 100% more atmosphere, the CO2 is only something like 0.03%, if I remember right. And maybe, yeah, I think that's right. Maybe it's even 003, but I can't remember. Again, don't take what I say as gospel, but I have asked that question. So when you do the math, why isn't it warmer? And so I just have to say, I don't know. I'd like to know the answer to that. And maybe I just need to take more time to investigate it. But it's an excellent question. And I did think about it. I just haven't figured out the answer yet. Sorry.
That is an interesting question. If you have any questions or anything, please put them in the chat. Tom, if you can you send to all attendees your email address? If they do have any questions, they know how to get in touch with you.
Yeah, is there a way that I can see who they are?
If you go to chat.
It's okay, I can do it in the chat. It's just my name. It's Thomas.Durkin. So
Here,
it's
I'll put it in there.
THOMAS.Durkin, DURKIN at sdsmt.edu.
Okay, I'll send it to everybody.
Okay, that'd be great.
Thomas.Durkin. Yes, that way, because sometimes maybe someone has a question after they leave.
Sure, and I'm on the global list for those who are state employees, but I know there's probably a lot of alumni that don't have our global address list anymore.
Yeah. Yep. No, I appreciate it. So, well, we're getting ready to hit the just hit noon. So I know everyone has to probably head out. If you have, as always, we appreciate your feedback. I'll drop a survey link in the chat there for everybody. If you can or have ideas about topics that you'd like to see, we do these once a month, so greatly appreciate it. And I will put the next upcoming digital department update. We are going to feature the physics department, and that will be August 5th. And then August 19th, that is also a Thursday, Geraldine Roberts from Facilities is going to be joining us, and she will be going over the campus strategic plan. If that's something you're interested in. We'd love to have you. So I'll drop some of these links in there for you. And again, this was recorded, so if you have any questions or need it, or or would like to have it, watch it replayed, we'll have it uploaded on our YouTube channel. So thank you for having us.
Thank you,
Oh,
Sarah
yep.
and
And Robert,
Dane,
I'll
for your
I'll
help.
copy your email and I'll send it over to Tom, or we'll get it over to you today. So you can have those slides.
Okay, and Sarah, I'll just put those 2 large video files on the H drive and send you the link to that on the
Perfect.
temporary files, and then you can upload them.
Yep. Sounds
Okay.
good.
Thanks a
Okay.
lot.
Well, thank you all. Have a wonderful day. Enjoy your afternoon and hopefully no rain, or hopefully rain where you're at. I don't know. So nice weather where you're at, but have a great day.
Thanks, Sarah. Same to
You're
you.
welcome. Thanks.
Bye.
Give 'em a-